Welcome to G Fun Facts Online. On the evening of November 10, 2025, a deafening roar shattered the rush hour calm near Dallas' historic Red Fort. A white Hyundai White 20 exploded, turning a busy street into a scene of carnage, claiming 13 lives and injuring over 20 more. But as the smoke cleared, investigators were faced with a profound scientific puzzle. This wasn't just a tragedy. It was a complex problem in physics, chemistry, and biology. Today, we're deconstructing the science behind the Red Fort blast investigation. When investigators from India's National Investigation Agency and Forensic Science Laboratory arrived, they treated the chaotic scene not just as a site of tragedy, but as a vast, open-air laboratory. The first principle of any post-blast investigation is that the crime scene itself tells the story. But in this case, the story was defined by what wasn't there. First, and most perplexing, was the complete absence of a crater. High explosive detonations, the kind you see in movies, are supersonic events. They release energy faster than the speed of sound, creating a powerful shockwave that gouges a crater into the ground. The smooth, unpitted road surface at the Red Fort site was a massive clue. It immediately suggested this was not a conventional, high-order explosion. An FSL official noted that even a standard improvised device would have left some pitting or fragmentation on the asphalt. Initial theories about a simple car gas cylinder failing were also quickly dismissed. The sheer destructive force was far too great. The second missing piece was shrapnel. Terrorist bombs are often packed with nails, ball bearings, or other metal objects specifically to maximize casualties. Their absence was another significant deviation from the expected pattern. It suggested either a different motive or a very different type of device. Forensic teams began the painstaking process of collection. Using tools like the Trace Explosives Recovery Kit, which can gather residues as small as 1/1000th of a gram, they swept the scene. Every fragment of the mangled car, soot samples from nearby buildings, and debris from the surrounding area were carefully bagged and tagged. Even after a powerful blast, unconsumed explosive material and chemical byproducts can cling to surfaces, providing a unique fingerprint of the bomb. With the evidence secured, the focus shifted from the street to the laboratory. Here, scientists had to answer the most critical question: what was the explosive? Based on intelligence from a related explosives seizure, the primary suspect was ammonium nitrate. This common fertilizer, when mixed with a fuel source like diesel, creates a powerful explosive known as ANFO. It's cheap, accessible, and a favorite of terrorist organizations worldwide. To confirm this, forensic chemists unleashed a battery of sophisticated instruments. First, ion chromatography. Think of this as a chemical sorting machine. Debris is washed with a solvent, and the resulting liquid is analyzed. The machine separates the different ions, and if ammonium nitrate was used, detectors will light up for its two components, the nitrate ion and the ammonium ion. Next up is the workhorse of forensic chemistry: gas chromatography mass spectrometry, or GCMS. This is used to find organic explosives, like TNT, or to identify the fuel component in an ANFO mixture. The gas chromatograph separates the complex sample into individual molecules, and the mass spectrometer bombards them with electrons, shattering them into predictable fragments. These fragment patterns act like a unique chemical fingerprint for each substance. Finally, techniques like infrared spectroscopy shine light on a sample. Different chemical bonds absorb light at specific frequencies, creating a unique spectrum that can be matched against a massive library of known substances, including all types of explosives. This process is painstaking, but identifying the explosive provides crucial leads, pointing towards the bomb maker's methods and potential supply chains. But knowing what the explosive was is only half the battle. The physical evidence at the scene, that massive fireball combined with the lack of a crater, pointed to a critical distinction in the physics of explosions: the difference between a detonation and a deflagration. A detonation is the hallmark of a high explosive like C4 or dynamite. The chemical reaction travels through the material faster than the speed of sound. This creates an instantaneous and incredibly powerful shattering effect, which is what carves out craters and pulverizes a bomb's casing into tiny, high-velocity fragments. A deflagration, on the other hand, is a subsonic combustion. It's essentially a very, very rapid burn. This is typical of low explosives, like gunpowder. Instead of a shattering effect, a deflagration creates a powerful pushing or heaving effect. The result is a large, rolling fireball that can still be incredibly destructive, but it's far less likely to create a classic crater. In the Red Fort case, reports suggested the bomb might have been